are recording. Okay, so for today, I'm going to talk about two completely different things. So first I'm going to go over the quantitative T1 and proton density and T2 star. Also T2 star, two flip steam method. Okay, is that enough acronyms? Okay. And then I'll talk about a completely different topic, which is SpinEcho EPI and BOLD, because there's some interest in this, especially for high resolution scanning. So we'll start with the quantitative T1 method. Now I talked about it briefly last time, but I'll go over it slowly enough so that hopefully it makes a little more sense. So we start off with, basically the overall picture is we collect we collect two scans, because all the quantitative methods rely on you only get a single number at each voxel from a scan, and that's not enough information to tease apart all the different features of the tissue that are actually causing that signal. It's just a mix of multiple things. And so if you want to do it quantitatively, you need to, at minimum, collect two scans. So the signal. So when we look at the signal equation, basically the amplitude of our complex signal for a gradient echo. So this is a two flip flash plus steam method. So if we look at the equation for flash, it's basically equal to the proton density. I call it in the notes. It's called A for proton density. So it's the proton density times the sine of the flip angle times 1 minus e to the minus tr over t1 over 1 minus cosine of the angle times e to the minus tr over t1. So that was and then there's a T2 decay term in there too, which we left off for now. That just depends on the echo time. So and if you saw one thing about this that's worthwhile, a little side note. If you wanna, when you actually plot this equation out, what do you get? You sort of get something that looks like, if this is the flip, you get something that looks like this. So this is the amplitude. And the peak of that, this is a useful equation just when you're sitting down at the scanner. So the peak of that is called the Ernst angle, and the equation for the Ernst angle, if you just basically solve this thing and find the max of it, basically the Ernst angle, so it is equal to, so that flip angle Ernst is equivalent to the inverse cosine, arc cosine of e to the minus tr over t1. So to find a flip angle, you have to know what the t1 is, but if you know approximately what your t1 is, then if you use this equation, you can figure out what is the flip angle that will give me the maximum signal. So that was just a little side. So sometimes that's called the Ernst angle. And you might want to, an example of where you might want to use this is if you're doing an fMRI experiment and you change the TR to 0.9 seconds. And you might want to find out, what is what should we use? What TR? TR is in there. What for this TR, what is the maximum angle going to be? So this would be, so you would have to use this, you'd have to, estimate this guy, and this is, we set this. So if we set this to 1.2 seconds, what is the flip angle going to be that will give us the maximum signal? So so now let's sort of approximate this. And what I mentioned last time, if we make a couple assumptions, like our TR is much less than T1, so we can sort of make some simplifications. So T1 might be 1 or 2 seconds, and if our TR is like 7 milliseconds or something like that, it's much less. And then what we do is we want to linearly approximate those exponentials, approx x, because we want two linear equations that we can use to simultaneously solve. And so the way you do this is, one way of doing this is with a Taylor expansion. You might have heard of this. I heard of it and forgot what it meant, but basically what that is at a particular point you calculate all the derivatives, and what is all different higher order derivatives, and what are those useful for? Those are useful for predicting what the signal is going to be a little bit later in time. So if you have, if there's some function like this, and at this point in time you can say, what's the derivative? Well, the first derivative is just the slope, and that will tell you, that makes a prediction into the future, what's going to happen. So you take this thing, sort of do a Taylor expansion of it, get all those derivatives, and then you throw out all the higher order terms, because the first derivative is usually going to be the one that's the most, the constant and the first derivative are going to be the largest effect. And then you can come up with this approximation. And so the approximation is that the approximation of what the amplitude of this thing is the proton density basically times the flip angle itself with no sine and cosine, and then with TR over T1 on the numerator, and the flip angle squared over 2 plus TR over T1. And so, like I said all the previous years, demonstrating my mathematical naivete, it's amazing that this thing is equivalent to that thing. It doesn't even really look much like it. But if you plot those out, you can just type these two equations into MATLAB and plot them out. And what you'll see is that, here's the first equation, and the second equation, it looks like the same thing. And as the flip angle starts to increase, you start to barely see that there's actually a little bit of a difference between them. But they're kind of amazingly similar. And why is that? Well, like take something like sine, and so there was sines and cosines in there. Where did they go? Well, if you look at a sine or a cosine, so here's a cosine. If you take the derivative of the cosine at 0, which is kind of like like a small flip angle, the derivative is 0, and it predicts the cosine is basically flat there. And then similarly, if you look at the sine, the sine for small flip angles is actually it's pretty linear. It just looks like it's extending up like a flat line. And so you can sort of get rid of sine and cosine because of what the derivative of sine and cosine is at each point along the sine and cosine. And so, so this is virtually the same thing, but the advantage of this now is that now we have a linear equation that we can simultaneously solve a second copy of. And so if you, so this is, this is our approximation. So this is, approximately equal to, there's our approximation. So now we just need 2 copies of it. And if we have 2 copies of it, then what we can do is we can solve for our T1. So we can just solve this equation for T1. So T1 estimated, equals 2TR. The signal that we get from one flip angle, so here's one flip angle, minus the signal we get from a different flip angle, because we have 2 scans, and then divided by the signal that we have from the second one, times the flip angle of the second one, signal we have from the first one times the flip angle of the first one. So there was a typo in the paper, the original. This paper that I'm talking about here is Helms. I have it in the readings if you want to take a look. Helms et al. 2008, or me 2012. So that's solving this equation for T1 given 2 scans at 2 different flip angles. And then we can similarly just solve the equation for our proton density. So this is PD, proton density. So proton density estimated equals signal 1 times signal, that looks like a 2, signal 1 times signal 2. This is where the error was in the Helms paper that they eventually corrected, over alpha 1 minus alpha 1 over alpha 2. Those are our flip angles, and the whole thing divided by the same thing above, S2 alpha 2 minus S1 alpha 1. Okay, so now we have 2 we have 2 equations that now allow us to solve for the flip angle. Sorry, given 2 scans, 2 sets of 3D data sets, signal 1 and signal 2, that were collected for 2 different flip angles, we can now solve for the proton density, the T1 and the proton density. So this is proton density here. So, but then there's the question of what about the flip angle? The flip angle's messed up also, and so we'll talk about how to estimate what the flip angle actually is on the right side. But we'll start off with where we get this. So there's 2 things we've got to deal with. We have to sort of figure out how to estimate what these flip angles actually are. We need yet another scan for that. But first, let's talk about what is the pulse sequence that gives us these 2 signals. So the pulse sequence basically is pretty much just a standard flash. So as opposed to like MP2 rage, where you did 1 inversion and then 2 whole collections of K-space at 2 different inversion times. This one is just a regular old flash. And one advantage of that is that it's the fastest possible data collection. Basically what you do is there's no gaps. It's just like fires away, just continuously collects data as fast as you can. So how does it work? You basically do a small flip angle. It could be either a slightly bigger one or a slightly smaller one, because we need 2 different flip angles. And we assume that we're in the steady state. That's what this this thing is 4, so assume we're in the steady state. And then we would do, for the slice select, and slice select fixer, and then we're going to be doing a 3D sequence, so there'll be a whole bunch of phase encode steps in the partition direction, in the second phase encode direction, and then there's going to be a bunch of phase encode steps in the phase encode direction. So this is, partition, slice, partition. So, the reason you call it partition is because it's a partition of k-space. It's not actually a slice. The scanner says slice, when you say, I want 176 sagittal slices, but what you're really programming into the scanner is, I want 176 steps in k-space. So it's not actually, so that's a partition. A partition is one sort of like step in z k-space. So here's the z gradient, and here's the y gradient. And then the one thing that's a little bit different about this sequence, the sequence was written by by Nicholas Weisskopf and Martina Callaghan in London. One difference about this is you collect more echoes. So when you go and collect a gradient echo like that, that's sort of the standard gradient echo. But what this sequence does is it does something that's kind of like EPI. It just goes back and forth across k-space. And so when you do that, so that's on the x gradient, on the readout gradient. So this one is the phasing code. This guy's a readout. So that sort of looks like EPI. And so what you do in EPI is, so here's the first gradient echo. You would normally get a gradient echo like that. So here's the actual FID at the beginning. So that's a typical gradient echo. But if you go the other way, if you turn the gradient on full blast the opposite way, what will happen, because at this point you will have wrapped up the spins to plus 128. Now if you go all the way the other way, you'll wrap them up you'll be back to here, back to negative 128. And then if you leave the gradient on, you will go back across k-space. So this sudden change in the gradient will essentially start unwrapping you the other way. This echo will be backwards like EPI. So you will have been at minus 128 and then plus 128, and then you go plus 128 to minus 128, and then minus 128 to plus 128. So you can do that a bunch of times and get a whole bunch of echoes. So why would you want to do that? So this one, the one we have is set up. We have it set up to do 8 echoes, so like 1, 2, 3, 4, 5, 6, etc. So one reason you might want to do that is because then what you could do is you could try to calculate the T2 star by fitting a curve to this, because this is going to be proportional to E to the minus T over T2 star. So that would be one way of trying to actually calculate a quantitative T2 star value, because we just have, at each voxel, we have 8 samples as the T2 is decaying, and depending on what the T2 is at that particular voxel, we could actually try to directly calculate what the fit an exponential curve to that and figure out what this T2 star time constant is, as opposed to just getting a T2 weighted image, which is sort of emphasizes T2. So that's a third thing that we could try to calculate using a slightly different method than this method for calculating the T1. And so basically what we would do is we would get sort of a T2 star estimated equals fit exponential. There's some constants in there that I didn't explain, but you can sort of see what you've got a bunch of data as the signal is decaying away, and so you can actually fit it. So okay, so that's good. And then what we do is we will be doing two different flip angles. So we'll do a small flip angle and a large flip angle so that we can have enough data to fit into this equation, the two signals to fit into that equation at different flip angles. But now we have the problem of the flip angles. And so the flip angles turn out to be not correct. So I mentioned before that when you actually look at, especially as you go up in Tesla, so at 1.5T, the flip angle is pretty uniform throughout the brain. But at 3T, what happens is, as the wavelength starts to get closer to the size of the head, so like the wavelength at 1.5T is pretty big relative to your head. But as the wavelength sort of narrows in, so it's going to be half as big at 3T, it gets closer to the size of your head, and it can start to sort of bounce around inside your head. And that can cause little hot spots, hot spots in your head where just very much like in a microwave. Not very hot. It's still, the frequency is a lot lower than a microwave. So a microwave is 2.4 gigahertz. Our frequency is only like 123 megahertz. So that's a lot less than a microwave. A microwave is 2,400 megahertz. We're only 123 megahertz. So so it's not as hot as, it's just like, but it's a little non-uniform, down maybe like about 25%. But that's quite a bit, because this whole equation here is based, on flip angle. The signal amplitude depends on the flip angle. And small changes in flip angle, like 1 or 2 degrees, 5 or 10% change in flip angle can cause a marked difference in the brightness. And so that's going to completely mess up our estimate. And so we would really like to know what the flip angle is. And that's separate from the question of, I mentioned last time, you have different brightnesses in different parts of the image from the receive field of the coil. So if the coil, a small coil, has a tendency to pick up one part of the brain more than another, that's going to change the brightness. But what we're talking about here is the flip angle caused by the body coil. And the body coil is quite uniform in its pickup, but when it sends something into the head, it actually sort of resonates differently in the head, and so the actual flip angle you get in different parts of the head, the B1 transmit field, is effectively different in different parts of the head. And so we need some way of estimating the B1 transmit angle. And so what we do there is we do another 2 scans. And so this is based on a paper which is in the readings if you want to look at it, by Giroux and Cloza, 2006. And so what they did for this paper was to collect spin echo plus stimulated echo. And so sometimes that's called STEAM. I can't remember what STEAM is. Stimulated echo, and I'm not sure. Sorry. But anyway, collect 2 different echoes with 2 different equations for those 2 echoes. And we went over those equations before. There's a typo in the notes, but I'll fix it here. So how does this work? So a stimulated echo requires 3 RFs. So we start off with, alpha equals 90, for instance. And so that's the RF pulse. And here's our GZ. And so what we're doing here is something that I talked about last time, which was an echo volume imaging. So we're doing something like echo planar, but we're collecting a whole volume, instead of just a single slice. So this thing is a slab select. This guy's it looks like a slice select, but it's set slab. I said slice. Okay, slab. So it collects a whole slab of data, and then we do a 180 here. So this guy is 2 alpha. 2 alpha equals 180. So here's that pulse. And this is a 3D scan. And so we're going to do, it's a 3D echo volume spin echo scan. So we're just slowly but surely using all the things that we talked about earlier. So you can do a spin echo EPI scan. I didn't draw that out, but that's a possibility. And how do you do that? You just do basically a 180. You do a 180, and then do an echo planar readout after that 180 at the right time. And so what's the right time? So the right time is going to be, if this is TE over 2, then that amount of time later is going to be where the echo appears, the spin echo. Because remember, if we wait the same amount of time after a 180, that will cause all the spins to come back into phase. And so right at this point, there's going to be a spin echo. But we need to collect some data. And so how do we collect data? Well, we sort of go to the corner of K-space here. And then we do a readout, but it's very, I'm sort of like jamming in 64 up and downs here. Okay, so we go back and forth. That's our echo planar readout. And then we've got a whole bunch of little blips right up here. Here's all the blips each time you cross. So, and then we set up so that we go through the center of K-space when the echo occurs. And so, oh darn, I put the blips on the wrong line. Okay, let's do this right. Sorry. So the blips are on this line. So here's the blips, because that's the GY, and then here's the GX. Now I just miss actual people in the classroom, because when I do stuff like that, usually somebody in the classroom will say, isn't that the wrong line? Okay, so here we are. We go to the corner of K-space, and we also have to go to the corner of K-space in the phase encode direction. And then we start doing our echo planar readout, and I've just compressed it in time. And then here's where we reach the center of K-space with the gradient echo, but also a spin echo. So it's basically a gradient echo plus a spin echo. But since the contrast is strongly affected by the value at the center of K-space, the overall weighting of the image will be a T2 weighted image, not a spin echo weighted image, not a gradient echo weighted image. So not T2 star, but T2. So that's all. So what this is this, what I drew so far was a spin echo EPI. So this is partition, and this guy is phase encode, and this is readout. So so the echo we get here, so this guy down here is going to be a spin echo. Spin echo. There'll be, not much there, and there'll be sort of a FID here. So that guy's a spin echo. So, but we want a spin echo and a stimulated echo, and so what we can do now is do another pulse. And so this other pulse is done, so let's draw those time in again. So here's, here's time tau, which is TE over 2, and here's, tau again, and here's TE. So now, if we do another pulse, we'll get a stimulated echo. So say we do another pulse right like here, not exactly tau, so let's just do it right here, just after we finished. So we might do a spoiler there. Okay, so just after we finished, we do another pulse, and this pulse is again equal to alpha, say it's a 90 degree. So now what's going to happen is we'll get another echo, and where will that echo be? So one of the problems, so this time here between the second and the third pulse is sometimes called the mixing time. That's what it's called in the literature, TM instead of TE. And it's kind of the mix, you can sort of think of the mixing time. That's like the suspended animation time where you put the spins temporarily into the longitudinal plane and they don't decay as fast. And then what will happen is tau amount of time after the third pulse, so here's tau amount of time after the third pulse, then we'll get another echo. So here there'll be another echo. And that one will be a stimulated echo. So we have to arrange to collect that, and so the way we arrange to collect that is we go to the corner of K-space again, do some more partition encoding steps. So we have got to do we have to do this whole mess that many times. And then, go back to the corner of K-space, go back and forth, collect all that data again. So we have a second readout. So this guy's readout 1, and then we have readout 2 from the same preparation of spins, and then we've got more blips. So here's our little blips. And so then this guy will be another echo. This guy is a stimulated echo with a different equation for it. So how do we use that? So the equation for the stimulated echo, I could write that one down. So the equation, so the signal for the stimulated echo is equal to basically our proton density, which we don't know, but we can just use a constant for that because it's going to divide out, basically. So sine cubed alpha, and the sine cubed, remember, comes from the fact that that this guy's twice as big as this. So it's if you make this one twice as big as this, instead of sine alpha plus sine of alpha over 2, if this guy's twice as big, then alpha is the same, so you get sine cubed. So sine cubed times e to the minus te over t1. Okay, so that's our spin echo amplitude, but the stimulated echo amplitude is different. So the stimulated, that's where I had the error in the equation. So the stimulated echo amplitude equals this proton density basically over 2 times sine, I had sine cubed, but it's It's basically, I had sine cubed, but I meant sine squared alpha times sine alpha, so it's basically sine cubed again, but times e to the minus te over t1. And is that yeah, t2. Okay, and then e, which one is t1? Did I, te, no, te over t2, yeah, okay, I got it wrong in the video, but it's right in the notes. Okay, everything's right on this one. So times t2 times e to the minus tm, mixing time. That's the one that is doing the t1 decay. So 1. Okay, everything's correct on here. I've straightened everything out. So sine cubed alpha times e to the minus te over t2. This one's basically sine cubed alpha times e to the minus te over t2 times e to the minus tm over t1, because that's the stimulated echo time. So now we've got those two equations. We can solve for the flip angle, and the flip angle is basically equal to the inverse cosine, arc cosine, of the amplitude of the stimulated echo times e to the minus tm over t1. So that the t2 thing divides out, divided by the stimulated echo amplitude. So now we've got a way to, so notice we've got to do two of these double echo guys. So we get a stimulated echo and a spin echo and a stimulated echo for one particular flip angle, but then we have to do, this was, for example, 90, but it doesn't have to be 90. But we then need to do a different flip angle because there might be some dependence on what the flip angle is as to the inhomogeneity of the flip angle. So you could potentially do a second flip angle, like a second flip angle here, a large flip angle and a small flip angle, and try to calculate what the actual flip angle. So this is our estimated actual flip angle. And once we get that, voxel-wise, remember this one, so this signal that's a stimulated echo and a spin echo signal is at each voxel, and that's different in different voxels. So we take that thing and substitute it in to these equations here. And then we simultaneously, we've simultaneously solved, this was the simultaneous solving of those equations. So once we substitute that in, then we can get our corrected estimate. So that's an example of how you would try to do everything right. So, calculate your actual estimated T2 by fitting to a bunch of echoes, collect two different flip angles so that we can solve for our T1 and proton density, and then collect some double echo 3D scans. They can be relatively low resolution because this doesn't change extremely rapidly, the flip angle inhomogeneity. Substitute that back into here to correct for that, because that's going to actually, and so why do we go through all this trouble? Well, the problem is if we're trying to look at, say, an area like MT, area MT is very highly myelinated, or area A1, MT area A1 is very highly myelinated. But the difference between that, versus the angular gyrus is an example that's not very myelinated. It's only like a 3% to 4% difference And if we're trying to distinguish other areas in between MT, really myelinated, and angular gyrus, really not myelinated, we need to be able to distinguish like a 1% difference. Or if we're looking for a change over time in somebody's brain, we need to distinguish like a 0.5% difference. And so for something like that, we really do need an accurate estimate. And so that's a little motivation for why you would go through all this trouble rather than just doing a regular old flash scan and just getting one scanner number out and dealing with it. Okay, so that was quantitative T1, two flip angle, multi-echo, flash, plus STEAM, meaning stimulated echo, plus spin echo method of trying to calculate the actual T2 star proton density and T1 that's actually quantitative. And these methods have been developed for many years. I mean, they were originally used by chemists. And so this is just like this isn't a brand new thing. People have been thinking about this for many years. This is just an example of what the current state of the art looks like. Okay, I'll leave that spin echo up here. So let's talk quickly about spin echo and bold. And so why on earth would we want to do that? So we said when you look at how does bold work? So bold is like blood oxygenation, dep. So no, there's an L in there. Blood oxygenation level dependent. There, blood oxygenation level dependent scans. So how does this work? Well, basically, we've got a blood vessel. Okay, here's a blood vessel. There's some blood in it. And if we want the blood to diffuse out the oxygen, not the blood, you don't want the blood out. If you want the oxygen to diffuse out of the blood vessel, then it turns out you need more oxygen in the blood vessel than is in the tissue. So the tissue is using oxygen, and as a result of the tissue here using oxygen, it somehow sends a signal to the blood vessel, we need more oxygen. And what happens is the little capillaries will dilate and let more blood into the part of the brain that's using oxygen. But now think about it. If the brain used up oxygen, then the oxygen is not going to, you need enough oxygen in the blood in order to cause a gradient of oxygen diffusion from here. So to maintain that gradient, you're always going to have more oxygenated blood in the areas that are using oxygen. So it's a little paradoxical, because you might expect if something used oxygen, then the oxygen level would be lower. But in fact, you've got to always make sure that you've got more oxygen than you're using in the blood in order to cause the signal to diffuse out. And so the paradoxical effect of the bold effect is that deoxy is the thing that kills signal. So deoxy kills signal, but because of excess oxy to cause diffusion, there's less deoxy. So therefore, signal goes up, because there's less of less signal killing. So the deoxy kills the signal, but what happens is in the places that are using oxygen, there's more oxygen. strangely. That's the fundamental principle of virtually all functional MRI. So, so because of this general argumentation, then what you want to do is, use gradient echo, use T2 star, for example, gradient echo, and that's why we use regular gradient echo EPI. So why would you want to use spin echo? So, and the fact that this argument is approximately correct is shown by doing a spin echo scan. So if you do this kind of a scan where it's an EPI scan, which is almost all gradient echo, except that the center of K-space is a spin echo because you collected the center of K-space essentially the same amount of time after an inversion pulse. The bold signal goes away. So why on earth would you want to do that, do that on purpose? And so the argument is, well, we might want to do it because of the following argument. So if we have a large blood vessel, so this is an argument from Buxton that combines sort of bold, spin echo, and diffusion. So we haven't talked about diffusion yet. Bold, spin echo, diffusion, T2 star. So if we have a large vessel versus a small vessel, we're not that interested in the signal coming from the large vessel because the blood in the large vessel is probably going somewhere else. So the large vessel it's got very rapidly flowing blood in it. The blood in the capillaries is very slow. Blood here is a rapidly rushing blood, spurting blood. And we don't really care about that because that's going somewhere else. What we really want to know is what's going on in the tissue around the capillaries. We don't really care about what's going on in the tissue right around the big blood supply because that's probably going somewhere else. That could sort of if the blood was going somewhere else, we might misattribute the signal from that blood that was actually designed to sort of be taken up by the tissue in a small capillary somewhere else. So we would like to select for the tissue around the small capillaries. So let's say we've got a bunch of magnetized blood in that large vessel. So what's going to happen, it will make sort of a kind of a cloverleaf pattern of magnetic field around the blood vessel. And the same thing will happen around a small blood vessel. So we have this kind of positive and negative cloverleaf pattern of the magnetic field around the blood vessel. Now let's consider a spin. So what happens is the spin is going to be diffusing around a little bit. So it's wiggling around a little bit, going different places because it's in the tissue. It's a little atom in the tissue. Now here's the same thing around a small vessel. There's a little thing sort of wiggling around, just Brownian motion going around. So what happens is in spin echo, because spin echo, remember, cancels, so gradient echo, we get T2 star because our static field not fixed. So any static field like the bold effect, not fixed. Whereas spin echo gives us T2 because fixed. So this looks more like a static field. More like static field. So and what is this? This is, you know, a magnetized blood vessel. Magnetized large blood vessel. So that looks more like a static field. And so what's going to happen is, if you do spin echo is going to fix it, because spin echo can deal with that kind of situation, which is kind of like, you know, why it kills bold, because bold is basically a static field offset from the deoxy, from less, less deoxy. So basically what will happen is, as the spin diffuses around, since it's mostly sort of staying about in the same strength of local magnetic field, spin echo will kill it. So spin echo kills, and spin echo over here, because the spin will go into a different strength of magnetic field, spin echo doesn't kill. So the argument is that basically you really want to do spin echo for bold, because spin echo will basically give you a signal that's mainly coming from from the tissue around the small capillaries. So remember, this is an argument this is not an argument about so this, argument applies to extravascular. So it applies to the tissue around, around the blood vessel. So here's the little capillary. So this guy is a capillary. So we're interested in recording from the tissue around capillaries, and there is some experimental evidence that suggests that the spatial especially, so one of the problems, another problem why people haven't done a lot of spin echo bold experiments is because it really kills your signal. And so if it really kills your signal, then unless you have a lot of signal to deal with, to work with, like for instance 7 Tesla, you typically don't want to mess around with it, because the signal is going to be too small, it will fall into the noise. But if you've got a whole lot of signals to start with, like 7 Tesla, so that means, lots of signal, because the bold signal is more or less proportional to the Tesla. So lots of signal, and what you can see is more spatial specificity of the spin echo spin echo versus gradient echo. So if you go someplace like where there's a visual map, and you sort of like look at the specificity of the visual map, which we know is there from a lot of experiments in animals, you can see that you have a sort of a finer representation of the visual map with the spin echo signal instead of the gradient echo. So this was, I admit, this is kind of like a tortured argument, but it just gives you some idea of the complex mapping between, the actual signal recording in the fMRI and, how it's coming out of the brain. Notice that none of this talks about the actual blood in the vessel, and there's a big signal coming out of the blood in the vessel too. This argument just applies to kind of spins, extravascular spins. So this is really just talking about sort of the spins that are outside, protons that are outside of the blood vessel, not the ones that are actually inside the blood. There's a big signal coming from the blood too, and that's all mixed in there with the signal that's coming that we're really interested. We don't really care about as much the blood. We sort of more interested in this. So that just gives you some idea of the complexity of what's going on. Now, if you actually look at the cortex, so here's a pyramidal cell in the cortex, what the blood supply looks like is you see these blood vessels sort of coming along the top, but then there's these little fine ones that go right through the cortex like that. And those are the ones we really want the tissue around those little fine ones that are going through there's a whole little sort of waterfall of little fine blood vessels going through the cortex that supply all the cortex. Those are the ones we're really interested in. Unfortunately, we get a lot of signal from these big ones here, but that's more contaminated signal because maybe there was some blood rushing here, but it's actually going over here. But we sort of picked up a big extra bolus of blood here, where really we want to know that the signal was coming out of this part of the cortex, not sort of just passing by there. So that's the kind of interest that people have in trying to use SpinEchoBOLD to detect the bold effect, with the hope of canceling out some of the signal that's coming from around the large vessels and focusing in on the little small capillaries. So that was way too long, but I'll stop here, David, and we'll take some questions.